Okay, so good to see everybody back for another day. um, so a couple of updates. I was on the phone with Pearson for a long time yesterday. They've still not fixed the problem for generating the homework. We're now on level 3 Pearson tech support, whatever that means. I'll probably just end up canceling homework 1, so don't worry about it. But I'll throw some of those problems into homework 2, maybe. We'll just kind of readjust. I'll try to make all the homeworks similarly sized and not like crazy long, but it is just an unfortunate set of circumstances. But anyways, so that's an update on the homework. I've seen lots of people forming groups, so great work there. Please continue to do that if you haven't already. I'll put you in one, towards the end of the week if they're not all formed. Today will be our first discussion day, so make sure you know where you're going for discussion. The TAs are going to do some more problems on like Pascal's principle, Archimedes' principle, and some of these other tools that we'll be learning today. So hopefully that's really helpful and makes the eventual quiz and homework. So you will have a quiz this week still. So hopefully that'll make the quiz more manageable and the eventual homework more manageable as well. Okay, so I think we can go ahead and jump into the slides. So we left off on buoyancy. So just to remind you, there's this weird phenomenon where really heavy things can float, such as cruise ships that weigh many thousands of tons, but really light things like pebbles will sink. And so it's not a question of the mass, as we described yesterday, it's a question of the density of the object. And so this is where we get into some of the details of what we will be calling Archimedes' principle, since he likely was the first person to figure this out. And so as we see on this picture on the left, when you have some submerged object, remember that the pressure as you go down in an object increases by rho gh, right? The deeper below the surface of a liquid you are, if that liquid is in a gravitational field, like on the surface of Earth, then the deeper below the surface, the more pressure you'll feel. And so if we look at this object, it has a force being exerted up on it, which is the P lower times that A, and it has a force exerted down on it, which is the P above it, so the P upper times the surface area of the top of the object. And because of this rho gh formula, whatever the height of the object is, so if this height is h, considering sort of a simple cylinder, then we can calculate what the difference in these two forces will be, right? So this lower pressure will be equal to the upper pressure plus rho gh, where rho, remember, is the density of the fluid, not the density of the object. And so the result here is that we have our total force, which is our P lower times A minus our P upper times A. And so because the P lower follows this relationship, we can plug that in and the P uppers are going to cancel. So we just end up getting rho GH times A. And H times A is just the volume of the cylinder. So we end up with rho GV, and you'll often see this called V sub, because this is the volume of the object that's submerged, the volume under the water. So you can imagine for a boat, only a small portion of the volume is actually under the water. So you're not going to use the whole volume of the boat to calculate this difference, just the portion of it that's below the surface. But for a fully submerged object, that's just the volume of the object. And so this is what we call our buoyancy force. And is basically the heart of Archimedes' principle. And so we calculated it here for a cylinder, but it turns out using some vector calculus tools that we're not going to get into for this class, you can show this is mathematically true for an arbitrary shape. But there's actually an intuitive argument for this that I want you to take a moment to think about, which is that, and it's described in this blue text here. Let me move this up a little bit. So if you imagine cutting out some weird shape of water, so you have a bathtub, and just in your mind, you section off some clump of water, whatever shape you want it to be in. Maybe you make it like one of those three-dimensional heart shapes or something. That section of water is in static equilibrium, right? Whatever forces are being exerted on it, they all have to cancel out, because otherwise that chunk of water would be flowing. But we know that if we let water sit still for a while, it'll all sort of come to rest. It won't be flowing anymore if it's just in a bathtub or something. So that little chunk of water in your tub is in static equilibrium, which tells you that its weight, mg, has to be balanced by some upward force, which is the buoyant force. And so if we think about this carefully, what that's saying is, so looking at this picture now, we're saying that the weight of the water, mg, has to be balanced by some buoyant force. And the weight of the water is just the density of the water times the volume of that little region, and then times g. So this is the buoyant force. And you can see that that is the same formula as this. It's just that when we're trying to calculate the buoyant force on some solid object, it'll be due to that water that it displaced, that used to be there in what was our imaginary clump. Now we've actually put an object and replaced that water, but the forces around the object are the same. Okay, so it turns out the geometry of the object isn't important, which is really crazy if you think about it. No matter what shape, like, we were taking advantage of this height h and the fact that the area is the same on the top and the bottom when we did this little small derivation on the the left side of the slide, but none of that matters because it turns out you can show this with calculus that all those, like if you have a more complicated shape, you can turn it into a bunch of cylinders basically and average them. But you can kind of get a feeling for that argument just by thinking about sectioning off a clump of water and imagining that it's in static equilibrium, so its weight has to be balanced by the forces of the water around it, which are what we call the buoyant forces. Okay, so buoyant forces aren't anything magical or mysterious, it's just due to the difference in pressure as you go deeper underwater. So if you go out into outer space and make a big bubble of water, which we talked a little bit about last time, and tried to float a boat on it, it wouldn't work. There's no buoyant force in outer space. And so it's just a result of gravity pulling down on a liquid, its pressure increasing deeper and deeper below the surface, and that causing a gradient, a difference between the pressure on the bottom of an object and the pressure on the top of the object, which causes the object to want to move up because it doesn't like this pressure difference. Okay, so this is actually the oldest bit of physics that we'll talk about in the course, because this is something that Archimedes figured out in ancient Greece. So it's like 3,000-year-old physics, which is kind of crazy because he didn't know calculus or anything, but probably one of, if not the smartest person of all time, at least that we have records of. So no, not a surprise that he figured this out. But anyways, any questions on this, this principle? And so you'll notice that the critical thing here is that it's the volume of the submerged object that's displacing some amount of fluid that has a density rho. And so moving on to the next slide. Oh, I guess we just get into an example, but as a result of this, it's the density of an object, or at least the density of the submerged part of an object, that determines whether or not it's going to float. Because what we have to do is we have to compare, I guess I'll just write up here. So if we have our object that's submerged, it has some weight mg, and it has some buoyant force FB. And the buoyant force is rho, this is rho of the fluid, just to be clear, times G times the volume of the submerged portion. Let's just imagine it's entirely submerged. So that's the buoyant force. And then mg is rho of the object itself times, G times V. And so you can see both of them, both the buoyant force and the weight of an object depend on the volume of the thing itself. So a more voluminous object will have more buoyant force pushing on it. They both depend on G, so they depend on what planet you're on. And they also therefore require there to be gravity for these forces to exist. And so the only difference is the buoyant force depends on the density of the fluid, because it's an effect caused by the pressure gradient in a fluid due to gravity. Whereas the weight of an object depends on the density of the object, right? It's like the mass of the object is what determines that force. And so what we can really just do is we can compare the density of the fluid with the density of the object, and that'll tell you if something will sink or float, right? If the fluid has a bigger density than the object, does it sink or float? If the fluid is more dense than the thing you're trying to put in it. Yeah, good. I hear some very slight whispers of float, which is correct. So a dense fluid is going to exert a large buoyant force, because the denser a fluid, the more pressure changes as you go below the surface. So the bigger that difference in pressure is between the bottom and the top of an object. Okay, and so if so this is float. If the fluid is less dense than the object, then it sinks. And if they're equally dense, which actually is very common, and the problem we're about to do is about exactly that, then the object is called neutrally buoyant. And this is a really desirable phenomenon for a lot of situations. So for example, if you're a scuba diver and you just want to kind of swim around a coral reef and not have to constantly try to be swimming up because you're sinking or swimming down because you're floating, it's really nice to be neutrally buoyant. And so what you do is you load yourself up with a bunch of lead weights so that you want to sink. And then you have a little vest that you wear that you inflate with air, and you put just the right amount of air in it such that you're not sinking and you're not floating. So you just sit there. And what you've done is you've changed your average density. By adding air in a vest, you've increased your volume without changing your mass very much, right? So density is mass over volume. So you've increased the volume, but the mass has basically stayed the same if you're just thinking about air. So you've decreased your density, and you can just keep decreasing it by adding more and more air until you get to the point where you're neutrally buoyant, and then you can explore the coral reef, whatever you were going to be doing. Okay, so fish do the exact same thing. And so let's do this example together where a fish is going to be the one trying to achieve neutral buoyancy. So fish have this thing called a swim bladder, which is basically like the vest that scuba divers wear. So it's a sac that the fish can pump air into and that is able to expand within the body cavity to change the volume of the fish. So with its swim bladder deflated, a 9.5 kilogram yellowfin tuna has an average density of 1,050 kilograms per cubic meter. Remember, water has a density of 1,000 kilograms per cubic meter. seawater actually has a slightly higher density, but let's just ignore that for this problem for now, because I don't remember what that is off the top of my head. It's swimming near the surface of the ocean. What volume of gas in milliliters must the fish have in its swim bladder to achieve neutral buoyancy? So they tell us its density and they tell us its mass. And this is the sort of deflated state. Okay, so how can we approach this problem? What are we trying to do here? I'm going to grab my calculator. Okay, so we want to make the object, or the fish in this case, neutrally buoyant, which means that we want, one way we could say it is that we want the buoyant force to equal the weight of the fish. But as we just saw, we could also just as easily, so equivalently, we could just say that we want the density of the fish to equal the density of the water. Okay, these are equivalent conditions because as we saw, the buoyant force, I'm going to write it down a few times today just so that it helps you remember it. The buoyant force is the density of the water times G times the volume submerged, which in this case is the whole volume for a fish. And that equals the mass, which is the density of the fish times the volume of the fish times G. So you can see the G and the V are going to cancel, and we get the same condition that the densities have to be equal. Okay, so they tell us the initial density of the fish. And remember that density, at least the kind of density we use in this course for the most part, will be a mass per volume density. The only time we'll use different kind of density, number density, will be when we get to the ideal gas law. And there it just often makes more sense to think about the number of molecules per volume rather than a mass per volume. But for now, mass per volume. And so we know the initial mass of the fish, we know its initial density. So we could find its initial volume if that's helpful, right? So this is just going to be m over rho. And so just to have that number, because I think it's nice to have, we can plug that into our calculator and we get a rather small number. So 9 times 10 to the negative 3 cubic meters. But remember that a cubic meter is pretty large. So saying that you have, in this case, like 1/100th of a cubic meter, that's a normal size for a smallish fish. And so now what we can do is we can say, what happens when we inflate a swim bladder? Well, we're changing the volume. Okay, so let's call this V naught, like the initial volume of the fish. Then if we want the density of the fish to be equal to the density of water, which is just 1,000 kilograms per cubic meter, then what we need to do is we can take the mass of the fish, we can assume that the air we add to a swim bladder doesn't really change the mass in a noticeable way, and divide it by V naught plus this V of the swim bladder that we're going to inflate. So that's going to be the fish changing its volume. And now we just need to solve for this V. So we can multiply by the denominator, and then we can distribute and subtract, right? So we're going to get something like V is, so 9.5 minus 1,000 V naught. And then all divided by 1,000. I did my math right there. And so now we can just plug that into our calculator. So I'll do that with you. So I get something like 4.5 times 10 to the -4 cubic meters. It's a good sign that it's smaller than the overall volume of the fish, unless it's a puffer fish or something. It would be pretty weird if it like doubled its volume through inflation. But now they want it in milliliters. And so this is a great situation where we can get some conversion practice. So does anyone remember what is a milliliter in terms of some length cubed? It's a really good thing to remember. Okay, I think I heard it. So a milliliter is a cubic centimeter. And so how many milliliters are there in a liter? Or sorry, in a liter it's 1,000 obviously, but in a cubic meter is what I mean. So there are 100 centimeters per meter. And then we have to cube that because we're thinking about volume. So there are 10 to the 6, so 1,000,000 milliliters per cubic meter. So we just want to use good old dimensional analysis, right? We multiply this by 10 to the 6 milliliters over 1 cubic meter, which is just a fancy form of 1. And our cubic meters cancel. We've now converted our units and we get our final answer. So the 10 to the -4 and the 10 to the 6 are going to leave you with a 10 to the 2. So this becomes 450 milliliters. Which, if you have experience with graduated cylinders, you can probably imagine, that's about the volume of like a small soda bottle. So pretty reasonable answer. Okay, any questions about this problem? I think it is, yes.
Is the depth of the fishes in the water?
That's a great question. So in terms of finding the volume, the depth doesn't matter. But in terms of the fish's point of view, it really does, right? Because the deeper you are, the more pressure is on your swim bladder. So the harder it is to inflate it. Okay, so for the fish, it's a lot more annoying to be neutrally buoyant if it's really deep underwater. And in fact, fish that live like in oceanic trenches and things tend to not have swim bladders. They use some other complicated ways to stay neutrally buoyant, or their body composition is just naturally neutrally buoyant. So muscle tissue is more dense than water, but fat tissue like adipose is less dense. So if you're sufficiently fatty, you can actually be neutrally buoyant even though you don't have any air inside of you. So that's one trick that some sea creatures use. But yeah, so we'll talk more, it's kind of weird. We're doing fluids now, but we're going to get to ideal gas law stuff when we start doing thermodynamics. So we'll get some more practice. We'll use some of our fluid equations, but we'll just be doing it more thoroughly. So it's a very prescient question. Okay, any other questions about this problem? I think it's one of those things where it's straightforward once you see it once, but it's kind of confusing like trying to set it up for yourself, right? So a lot of that just comes down to getting some practice. So I wanted to talk about another situation that you might encounter, and there are actually some more slides about this later when we get to viscosity, probably tomorrow. So don't worry about the formulas too much at the moment. But you can imagine dropping a pebble like in this picture here, and that got me thinking at least about how do we find the velocity that pebble falls at. So at first it sounds like you would just think, well, it's a falling object, so the weight is what's going to cause the object to fall, and you may naively think that would be the only force, or maybe you're like, okay, there's also going to be some friction with the fluid, but Now we know there's also a buoyant force. So even for a sinking object, this is a really critical idea. Even for a sinking object, there's still a buoyant force. It's just that when something sinks, the force of the weight of the object is larger than the buoyant force. And so that's why even when you breathe all the air out of your lungs so that you sink, and you go in a pool and you're like running on the bottom or something, you feel kind of like weightless, not quite fully weightless, but you feel lighter than you usually would. And that's because the buoyant force is lifting you up. Even though you're sinking in that scenario, you have an effective weight that's lower than your normal weight. And so when something's falling through a fluid due to gravity, there are actually three forces involved. There's the weight of the object, there's the buoyant force, which is what we've been talking about, and then there's also the drag through the fluid. And so we will be learning about drag in this class, and it's one of the things I want you to understand. And so I'm not going to get too into it in this slide because I realized that the book actually wants us to talk about it tomorrow. But basically, there are two ways that drag can work in a fluid. So drag in a fluid can either follow this kind of equation, which is called linear drag. So this would be F drag is some number B, some constant, which is based on what kind of fluid and what shape the object is and how big it is, its area, times the speed that it's going. So the faster you fall through a fluid, the bigger the drag force is going to be. It's hard to move fast. You can imagine if you're trying to run and it's a windy day, you really feel it as you start to speed up. And it becomes more and more obvious that the wind is pushing against you the faster you're moving against it. Or the faster the wind is blowing naturally, exerts a larger force on you. But in some situations in fluids, the force is quadratic. So for air, the drag force is almost always quadratic. And we're going to learn how to tell when it's which of these probably tomorrow. But depending on the situation, so depending on the size of the object and sort of how viscous, how frictiony the fluid is, the drag will be either one or the other of these. It'll either be some numbers times the speed or some numbers times the speed squared. And what this allows you to do is to talk about a terminal velocity. Okay, so because the drag force gets bigger and bigger as the object speeds up, if you drop a rock into a pond or something, sounds like the most boring experiment ever, but it is interesting, sort of. Then the drag force will just keep getting bigger and bigger as the object accelerates until you get to a point where the weight and the drag force and the buoyant force are balancing each other. So at terminal velocity, we're no longer accelerating. That's why it's called terminal velocity. And so what that tells you from Newton's second law is that the downward force, which is the weight, so mg, equals the drag plus the buoyant force. Okay, and so for a moment here, let's think about linear drag, which is going to be more common in liquids, especially for small objects. Then in that case, we could say mg is some constant, some drag constant b times the velocity plus, and then the buoyant force, remember, is the density of the fluid times g times the volume that's submerged. In this case, the object is sinking, so that's the whole volume. And I'll put some little lines on this to remind you that's the volume and not the velocity. So now we could just solve for this velocity. This is the terminal velocity, since when we set up that equation, we assumed that there was no acceleration, right? We just wrote the forces, we didn't write equals ma on the side. So for this linear situation, the terminal velocity is mg minus rho fluid G times V over that drag coefficient B. And so that'll tell you if you drop a rock, into a pond, it'll keep speeding up until the drag force gets big enough that now it's no longer accelerating, and it'll just continue at this terminal velocity, all the way until it hits the bottom of the pond, and then it'll stop. Okay. And you can see it's going to be very similar for quadratic drag. It'll just, instead of the B, you'll have a C, and you'll have a square root around the whole thing. So it's a little more gross, but gets the job done. Okay, so any questions about this terminal velocity stuff? I know did you talk about it at all in 3A? It's sometimes a 3A topic. Okay, a little bit. So that's good. I think it makes more sense in this class, because here is where we're supposed to learn about fluids. So I think it's, more likely to be part of the questions you see. Okay. So now we're going to move on to the next topic, which is surface tension, and along with that, capillary action and wetting angles and all of this stuff. A lot of professors like to skip this material in 3B. Personally, I think it's like some of the most important stuff we do in the fluid section, because it's so relevant in, like, if you're working in a lab and you're using pipettes or something, this is what's affecting all of your measurements, and what's, you also just see the results of surface tension all around you once you start looking for it. Like, I was driving here this morning, and there was a bunch of condensation on my windshield, and I noticed that it all formed these little droplets, right? You've probably all seen this before. When water is on the glass of your windshield, it'll form little droplets that'll kind of obstruct your vision. And that effect, that sticking of these water droplets onto the glass, and the fact that they form these little spherical shapes, they're all results of these surface tension, adhesion, cohesion type forces. And so that's what, I really want to spend some time talking about this. I do expect you to know how these things work. And I'll, be your guide to walk you through them. You'll also have your discussion section to help as well. But anyway, so to dive into it, to motivate this more than already, perhaps, you may have seen little bugs like this walking on the surface of a liquid. And what's really cool about these bugs is that they don't actually have any part of their body submerged beneath the liquid. So there's no buoyant force. Remember, the buoyant force is rho GV submerged. Okay, so how do they float? And it's not a buoyant force. It's not due to a pressure gradient. It's all a result of molecular forces between water and the bug in this case. Okay, so we'll see some more details on how this works in a second. But for now, it's good to just define what we mean by surface tension. So if we imagine making a bubble, so this little blue region is supposed to be like a bubble, some sort of thin film. Then as we pull one side of the bubble, we can stretch it out, and that bubble will expand, if we do this gently. And we could ask ourselves, what is the tension force holding this bubble together, basically? Okay, so I'm pulling on this like brass rod here, and there's some force opposing me, so that'll stabilize that force, which is this tension. So this tension is acting all along the length where the water is contacting this metal rod, for lack of a better term. And so what you'll often see done is to ask how much of this force is there per unit length of the contact region. So where the fluid is touching something. And we'll see lots of examples of this. So don't worry too much if you're like, what is it touching? What is the length? Those are all very valid questions. But it turns out that how much force a liquid applies per length is some measurable constant based on the material composition of the fluid. And we call it gamma. And this is what's known as the surface tension. So when a physicist says the surface tension of soapy water is some number, this gamma is the number that they're talking about. So it's really a tension per length, okay? And it's just convenient to parameterize it that way, because then we can just have a big table of them, as you'll see in a moment, for every different material under different conditions. Okay, and so a really important property of these films is that, so you can imagine if this, instead of a bubble, imagine this were like a sheet of rubber bands and we were stretching it. So you should have learned in 3A that when you stretch something like a sheet of rubber bands, it follows Hooke's law. The farther we stretch it, the bigger that force trying to pull it back is. It gets harder and harder to stretch those rubber bands as we pull them out. So if we plotted how far we stretched it versus the force, for a rubber band, it would be something like this. It's just going to increase as we stretch it. So this is for us something like a spring or a rubber band. For surface tension, it's actually nearly constant. So as we, and we can think about why that is, as we pull this fluid thinner and thinner, what happens is the liquid, so even for something like a bubble that looks really thick to us, from a molecular standpoint, it's actually, has a ton of molecules in the middle. And so as we stretch this bubble, the molecules in the middle can move to the surface. And over time, they'll just allow the surface to continue to expand. But the only thing that's contributing to the force is how long that contact length is, L, which isn't changing in this situation. We're just stretching it sideways, but we're keeping that length the same as we stretch it. Okay. And so I think that's all that I want to talk about on this page. Are there any questions about sort of, I guess I haven't explained where this comes from. So when we have a surface, we can imagine one of these little molecules. So if, let's say for water, for example, just so I don't keep saying like X molecule. So one of these water molecules, if we imagine one in the middle, it's kind of being pulled on in all different directions by its neighbors, right? Especially for water, which is a very weird liquid for a lot of reasons that we just take for granted because it's everywhere. Water has really strong intermolecular hydrogen bonds. And so the water molecules are all pulling on each other, jostling with each other. And so if some molecules in the middle of that fluid, it feels that in every direction. But if it's on the surface of the fluid, then on one side, there's just air, which isn't exerting those same hydrogen bond forces. And so as a result, the liquid on the surface of the water feels, or I should say, it's in a higher energy state. So it doesn't like to be there. It wants to be surrounded by other water molecules so that the forces are all acting in every direction. Because on the surface, there are more forces acting this way. So the molecules want to be pulled back inside. And it's this phenomenon that leads to surface tension, because we have these water-air boundaries and some contact length. And the molecules that are along those boundaries are feeling some unbalanced set of forces, the result of which is this surface tension. So the book goes through this same explanation, but you can maybe get it at your own pace, which can be helpful. Because it is kind of a weird phenomenon, but it all comes down to the fact that surface tension, you see it when you have an interface between a liquid and a gas, somewhere where a liquid and a gas are touching each other, because at that point, that boundary, the molecules of the liquid on the surface are feeling an unbalanced force. And so that's what leads to the surface tension. Okay. So we'll see some examples and maybe it'll start to feel more reasonable. So this table on the left here actually gives values for gamma. So that's what these numbers are. And as you can see, they're in force per length. It's just that surface tension is a small effect. So they're often given in millinewtons per meter. And so that's what this mn per m, somewhat confusingly, this millinewtons per meter. So very small forces, but strong enough to be really important in a lot of situations. And so let's do this problem together to get some practice with them. So we have a U-shaped frame, but here the end that's free to slide is on the bottom. Okay, and so it has some weight, mg. Oh, we're losing some calculators. It has some weight mg. And then there's a surface here. And so that surface applies a tension force. That was terrible. There we go. That surface applies a tension force. And remember that gamma is T over L. So this tension force is gamma times L. And so they want the situation where a film of soapy water across the frame is held down by the weight of the 10 centimeter long slide. So they want the situation where there's no acceleration again. This is just an equilibrium type problem where the weight and the tension force are balanced. There's one complication to this that really trips people up. And so I'm going to walk you through why it happens. It turns out for this situation, there are two surfaces. So I want you to think about this. If I have a little droplet of water, there's water inside, there's air outside. So there's only one surface. There's only one boundary where the water touches the air. Okay, good. For a soap bubble like this, whether it's floating in the air or whether it's attached to a frame, there are actually two surfaces. Okay, so think about a soap bubble first that's floating. There's air inside, and then there's the water soap mixture of the bubble, and then there's air outside. So that's one surface inside and one surface outside. Okay, so when we're doing calculations with soap bubbles, the surface tension is actually going to be twice as big. And similarly here, we have this metal ring, this metal rectangle, and there's soap in the middle of it, soapy water in the middle of it. So there's air, soapy water, and then air. So there are two surfaces. And just to give you another example, we could imagine a little gas bubble. So like when you boil water and you see the little bubbles coming up from the bottom of the pot, those have one surface because there's air inside or water vapor inside, and there's liquid water outside, so only one surface. So counting the number of surfaces, you'll still get a pretty close answer, even if you mess this up. And if it's the final or something, you'll still get lots of partial credit if you do everything else right. But it's important to, if you want to get it all perfectly right, to understand that the number of boundaries between the liquid and the gas determines the strength of that surface tension force. So it can easily be doubled just by having a thin layer that has gas on either side, because then the molecules on the left side are unhappy because they're on the surface, and the molecules on the right side are unhappy because they're on the surface. So they're both applying a force to the system. Okay, so all of that is to justify me chucking in the number 2 here because there are 2 surfaces. Okay, so now we can just do our problem, right? So just to do this one out more thoroughly, we can say F equals ma, but of course our A is 0. So our force upward is 2 gamma L, and our force downward is mg. And so these 2 things have to be equal. And they want to know the wire's mass, so we can solve for that. We get 2 gamma L over g. And now we can just plug in. So the gamma, they tell us that this is soapy water. So we come over here to soapy water. So this is 25 millinewtons per meter. So that's going to be 0.025 newtons per meter. Be careful with those conversions. The length of the wire is 10 centimeters. So that's going to be 0.1 meters. And then G is 9.8 meters per second squared. So you can see that at the end of the day, the units are going to cancel nicely and give us kilograms. We can plug all of this in. I'll do it with you here. And you get a mass of 0.5 sorry, this is already in. So let me just write out my work here so that it's, so I get 5 times 10 to the minus 4 kilograms, which we could say is 0.5 grams, or we could say that's 500 milligrams. So a pretty small mass, but totally reasonable for a thin stretch of wire. So a soap bubble could very reasonably hold up a thin bit of wire, forming a little rectangle like this. And as we'll see, that's also similar to the mass of like insects and things that float on the water, or I shouldn't say float because it's not buoyancy, that walk across the water using surface tension. Okay, any questions about this one? So just to help you, part of the difficulty of physics is just identifying when you're like what type of problem something is. And so if I saw this problem, just to give you some experience with this, when you see like a film of soapy water, that's a good indication that maybe you're interested in surface tension, right? A thin film, or if you see a bubble, if they use these sorts of keywords, or something is, floating without being submerged, these are all indications that the problem has something to do with surface tension. And so you should be thinking about this gamma is T over L formula. Okay, so we're a little over halfway through the class. So actually, I was meaning to do this yesterday. I want to give you like a couple minute break. So if you want to stretch, I'm going to stretch, and talk to each other, whatever you want to do. I just know an hour and a half is like too long to sit still. So a couple minutes. Oh yeah, so haven't gotten it set up yet. But don't worry about it. Everybody's having to take off. Yeah, that's what I was gonna. A does equals. So there's things. Okay, so hopefully that helped get some brain fog to go away. But I do want to jump back in this because I guess we're not behind schedule, but I definitely want to get through surface tension today so that we can talk about fluid in motion tomorrow. So we'll do another problem just because I think when something is confusing, it's good to do more problems. So this one is very similar to how a bug would float on the surface of some pond or something, but they just frame it as a needle because physics books are often boring. But anyway, so you can see in this picture how none of this needle is beneath the surface of the water. So there's no buoyant force present here. So the only two forces, or sorry, yeah, the only two types of force here are the weight pulling us down and the surface tension pushing us up. Okay, and so let's go ahead and look at these two. So I'll write it properly this time. A equals 0. I get a little slash happy sometimes. So what that tells us is that the weight of the needle has to be balanced by the total upward force on this object. So what is that force? Well, we have surface tension on each side of the needle. So there's going to be a factor of 2. And then remember that the surface tension is defined as the force over the length. So we're going to have some gamma L in order to actually get that back to the form of a force. But then we also have this so-called like wetting angle or contact angle. So this is related to the strength of the surface tension, basically, and the intermolecular forces not just within the liquid, but also between the liquid and the object that's being repulsed. But here, the basic consequence of this is that we have only to worry about the sine component. So the sine phi component. Because the cosine phi components are just pulling the needle sideways and they're being balanced in the x direction. But if we're trying to find effectively the mass of the needle here, and then additionally its diameter, then we need to know how the vertical forces are behaving. Okay. So this is our setup, and you might notice we don't know what this phi is. And so we have to hop on over here. And they don't give us a water iron contact angle, but I think it's fair to use something pretty similar to water glass. So maybe 30 degrees. And that'll also make the math a little bit nicer. Okay, so now we can just solve for the mass by dividing both sides by g. And when we take sine of 30 degrees, we just get 1/2, which is going to cancel with the 2. And we end up getting gamma L over G. So this needle is floating in water at 20 degrees Celsius. So we come over here and we find the surface tension for water at 20 degrees Celsius is 73 millinewtons per meter. This is actually a really fun fact that surface tension is very dependent on temperature. And that's part of the reason, but not the whole explanation for why it's easier to clean things with hot water than with cold water. Because hot water has a lower surface tension, so it's easier for it to spread out on a liquid. It's not going to ball up into spheres quite so much. Hot water also just dissolves things more easily, right? That's something we learn in chemistry. But anyways, so our gamma is 0.073 newtons per meter. The length of this needle is 4 centimeters, so 0.04 meters. And G is 9.8 meters per second squared. You can see the reason we need to convert those quantities is because G already has base units in it, right? Meters and seconds. So we want to make sure that our other units are compatible with that. And so we can plug that in here really quick. And I get another really tiny match. So this is 300 milligrams, but again, totally reasonable for like a sewing needle that you would have it at home. So normal mass for such a thing. And then now they just want you to practice a little bit with density. Okay, so they tell you the density of steel is 7,900 kilograms per cubic meter. And so if this is a cylinder, then its volume is just pi r squared times its length. Or we could just write that as pi d squared times its length over 4, since they want you to find the diameter here. And the density is the mass per volume. So if I guess I'm going to end up writing up here. So if density is the mass per volume, then volume is mass over density. And we can replace volume with pi d squared L over 4. And we can solve for d. We get the square root of 4m over pi L rho, and this is the rho for steel. And so we can quickly calculate that as well. So 4 times our mass, which is 3 times 10 to the minus 4 over pi times the length, which is 0.04 times the density of steel, which is 7,900. And so I get a diameter of very close to 1 millimeter, which is pretty reasonable for a needle. You know, you can imagine pencil leads are often like 0.5 millimeter in diameter, or 0.7 millimeters. So that's about how big a needle is. And so this is something you can do at home, is just take a needle, gently rest it on some still body of water, and it'll magically stay there without actually any buoyant forces acting on it. So it's not floating in the normal sense, it's just being repelled by the surface tension. Okay, so I know that's a bit of a long calculation. Yes. So where this 2 comes from? Okay, good. So you can see on this needle, so we have our needle and we have the water here. There's a boundary on the right side of the needle all along that length, and there's a boundary on the left side of the needle all along that length. So that's where the factor of 2 comes from. I know these factors of 2 are really annoying. They trip me up sometimes too. But we have to carefully ask ourselves, how many places are there where the water and the air are touching that are also touching something else, which is the object that's going to feel that surface tension? If there's nothing else touching the water-air boundary, it still is exerting a force. It's just that it's not going to cause something to float or hold up some bit of wire or something. You know, we'll actually talk about an example in a moment where there's not a third object. It's so for bubbles, it's only that we have the liquid and the gas. So we just care about that contact boundary. But here, you know, we have to ask ourselves not only where does the liquid touch the gas, but also where does that additionally touch the needle. So we need all 3 things. And if we ignore like the ends of the needle, which are very, very thin, so they're not going to do much, then it's just the length on the right side and the length on the left side. And so that's where we get our factor of 2. Okay, so that's a very good question. Any other questions about this problem? Yeah. Yes, so you do want to use 3 times 10 to the negative 4 kilograms in that when you're finding the diameter, because they give us the density of steel in kilograms per cubic meter. Okay, so if you had the density of steel in some other set of units, you could use those units in the square root. You know, generally, I just would advise you to always convert to kilograms, meters, and seconds, and newtons and such before you plug into equations, because that's the easiest way to ensure that all your units are compatible with each other and happy and everything. But yes, in this problem, it's a necessity because of the units density are given in. Yeah.
So you say it's sort of tangent, so we don't care about buoyancy forces.
Correct.
So if correct attention, they have this large part that we don't care about it.
Yeah, so you ask, this is a good question. So generally, surface tension only happens on the surface. So generally, if something is partially submerged, surface tension won't make much of a difference. Buoyancy forces are almost always going to be much, much bigger than surface tension forces. And you'll rarely see both at the same time. Now, I could imagine making a hard physics problem for you all, where maybe you have an object that has 2 components. You know, maybe you have like a leaf where the surface of the leaf is like thin in some region and supported by surface tension, and thicker in some other region and supported by buoyancy. And so you can have systems that have both, but it won't be both at the same location. It'll be some part of the object is supported by surface tension where it's very thin and small, and some chunkier part is supported by regular buoyancy forces. Okay, good question. Okay, any other questions? This is why I want to do problems. You know, a lot of professors would rather just not do this section at all because it's a bit hard, but I think it's very relevant physics. Oh, yes.
Is there any way to know the contact angle like through that, or is there just
It's something that'll be given to you or through a table. That's a really good question. So contact angles, I'll talk more about in a second. As you saw, I kind of had to skip to a slide ahead to get a value for them. Contact angles really depend on the detailed molecular composition of the surface of the material. So technically, water and glass have a contact angle of basically 0. So if I put a droplet of water on a microscope slide, it should completely flatten. But we know that doesn't usually really happen. Like if you've played with a microscope in a lab, it's often hard to get the water to really distribute. And that's because of microscopic either abrasions in the glass, or if you get a little bit of oil, if you touched it, then that oil is hydrophobic, so that'll change the contact angle. So contact angles are very tricky business. So contact angles also are the reason that you have a meniscus in like a graduated cylinder. And my best advice with contact angles is to avoid having to deal with them. So the way that you do this, let's say you're trying to measure like with a pipette, is you have the type of pipette that little top portion of the water is never dispensed. Okay, so you can design a pipette where it sucks in water and it expels water, but it never gets rid of that top layer of water where the contact is happening, where the meniscus is. And that way you can actually have precise measurements without having to worry, is there some small abrasion on the glass of this, pipette tube, or is the plastic the day that the factory made it a slightly different composition? It can be very annoying. So avoid it if you can is the practical advice. But yeah, there's no good way to calculate it. Even with very advanced numerical simulation, it's hard to calculate contact angles. Okay, so now we're going to talk about the example of droplets, which are really important, and they're kind of nicer than the previous problems we did, because you don't have to worry about a third object, right? When a needle is being supported, you have the gas of the air, the liquid of the water, and the solid of the needle, and you have to find where all three are touching each other. With a bubble, you only care about the liquid and the gas, okay, that boundary, and that's what holds the bubble together. So, for ants, this is a really important fact of life, because they're of a size where water bubbles are like the primary form of water. And so they'll often even sort of scoop up water as if it were like a gel. It's really cute if you want to find some videos of it. And they can kind of carry it in their mouth as a little like gel ball of water. And it's almost like when you go buy a Jello packet or something, or a Jello cup. And that's because at these small scales, the surface tension forces are really noticeable. They're really important. And so they cause water that would normally want to spread out due to the force of gravity, they cause it to ball up. So on these small scales, surface tension is stronger than gravity. And similarly, if you're in outer space where there's no gravity, then surface tension is the only force in town. So that's why in space, even large quantities of water will form bubbles. Okay, so anyways, we have this little diagram here, which is yet again pilfered from the textbook. So if you want to see more of these. So if we look at, so imagine that this is a solid bubble of water, like this picture of the ant here. So there's only one surface, which is the surface on the outside of the bubble, right? Between the water and the air. And before I get into the details, the reason that water forms spheres is because a sphere is the shape that has the least possible surface area. Okay, you can imagine if you had a cube instead that was a some volume, that the corners cause there to be more surface area in those regions. And if we imagine that the liquid is trying to pull itself together to minimize how much water has to be in the unfavorable position where it's in contact with air instead of just surrounded by its buddies, then that water is going to want to pull in to a spherical shape, which is why these bubbles form in the first place. Okay, so it's an effort to minimize the number of molecules that have to be on the outside of on the surface of the water. Okay, so if we look at 1/2 of the sphere, then that gives us a way to actually figure out some of the forces involved in creating a bubble. And there's a really unintuitive result that comes from this. So looking at the left side, we have 3 forces. So there's this force Fr. So this is due to the pressure outside of the bubble. And that pressure is pushing on that whole area of the sphere. So you might say, well, I remember the surface area of a sphere is 4 pi r squared, or I look it up, whatever. And so that's half of a sphere, so that's 2 pi r squared, but not so fast, because some of that pressure is pushing down and some of it's pushing up because that sphere is curved. And so if you actually do the math carefully, which unfortunately requires calculus, so I'm not supposed to do it with you, then you get that the interesting area here is just pi r squared. So the area that's actually causing a force that pushes to the right for this Fr vector is only the cross section pi r squared that you have on the inside as well. So the best I can do, I think, intuitively, is to imagine that some of that, the real area on half of a sphere is 2 pi r squared, but some of that is causing forces that push downward or push upward, right? Because the pressure is pushing in all directions. So the part that's pushing to the right is just based on sort of the cross-sectional area pi r squared. You won't be asked to derive this, but you will need to know how to work with the formula that we're about to get. Okay, so then there's also this FL. This is due to the pressure inside of this bubble. And again, it's being multiplied by pi r squared. Here, that's more obvious because it's pushing on that circle from when we cut the sphere in half. And then finally, there's this surface tension force. And this is acting all the way around the circle. So that's our L, right, remember, surface tension, we have this formula, gamma is T over L. So T is gamma times L. So we just have to ask ourselves, what is the length over which this surface tension is acting? And that is just the circumference of the sphere, 2 pi r, because that's where the water and the liquid are touching each other. Okay, and that's the only point on this left side of the sphere where the surface tension can pull things, in this case, to the right. Okay, anywhere else where it's touching, like over here, it's pulling things, at some angle, and that force gets transmitted until the rightward component is exerted on the edge in this picture. Okay, so now we can just put our pieces together and we can see how the pressure changes as we go inside of a droplet of water like this. So if the droplet isn't accelerating, then Fr plus the surface tension has to equal FL. So you can see how Fr is pointing to the right, the surface tension is pointing to the right. So they have to be balanced by this inward pressure pointing to the left. Okay, so now we can just plug in each of these terms. So we have P out times pi r squared plus gamma 2 pi r equals p in times pi r squared. And if we want to find what p out, or let me actually. If we want to find what P in minus P out is, so that'll tell us how much bigger the pressure is inside this droplet than outside of it, then we want to subtract P out times pi r squared from both sides and divide by pi r squared. And so we're going to get gamma 2 pi r over pi r squared. And we'll have some things cancel. The pi's are going to cancel. One factor of r is going to cancel. And so we get 2 gamma over r. Okay, so I know derivations can quickly be boring, or you can easily be lost in them. But let's think about the implications of this. So P in minus P out. What is the pressure outside of a droplet if it's just sitting on your car's windshield or on your desk or something? What's that pressure outside of the droplet due to? No takers? Okay. It's just the atmospheric pressure. So there's, we have a droplet of water, there's air around it. And if you're on the surface of the earth, then that air has a pressure of 1 atmosphere. So P out is just 1 atmosphere, or 100,000 pascals. And so this P in minus P out, this is actually the gauge pressure of the inside of the droplet, right? If I took a pressure gauge, it's calibrated such that it says 0 pressure at sea level, because we want to kind of ignore the effects of the atmosphere in most applications. But if we put it inside of this little droplet, it would have to be a very cleverly designed pressure sensor. Then we would get this gauge pressure 2 gamma over r. And the important thing here, so obviously as the surface tension of a fluid increases, so does the pressure inside these droplets. So we can see that for water, which has a very high surface tension, these droplets are going to have a larger pressure. Whereas for something like ethanol, which is just drinking alcohol, it doesn't tend to form droplets. And so the pressure isn't large enough to actually keep them together. Similarly, we see that radius is in this, the radius of the droplet matters, but it's an inverse relationship. So smaller and smaller droplets actually have larger and larger pressures. And so by the time you get water droplets that are really, really tiny, like, for example, the droplet that an ant might pick up with its little pinchers, that can have a pressure of, half an atmosphere. So significant pressure compared to a larger droplet that has almost no pressure inside of it. So if you were to be in one of these sci-fi novels where they make big spheres of water out in outer space and go swimming in them, you can see that those spheres would have a large radius if you're able to swim inside of them. And so the pressure would be almost 0 inside the sphere. So it would really be a magical swimming experience. You wouldn't have to, pop your ears or anything. You could be completely in the center of the sphere and you would just feel the same minimal pressure. And you also see that this pressure doesn't really depend on where you're at in the sphere. It's going to be basically 2 gamma over r, whether you're in the center or pretty close to the outside. So it's not like our ρgh formula due to gravity, where the deeper you go, the more pressure you have. It's really just due to these surfaces, or the one surface here, pulling you inwards. And so on that note, so this is for a 1 surface object. We could also find the gauge pressure for a 2 surface object, and it turns out it's just double this. So it's 4 gamma over r. I'm not gonna bore you with the whole calculation, but basically this tension in that case would just have a 2 whacked in front of it. For something like a soap bubble where there's air inside and air outside, we have 2 surfaces, so it's twice the surface tension. Okay, so that's bubbles. You know, the only real formula you need for them is this 2 gamma over R or 4 gamma over R, depending on what kind of bubble you're working with. Okay, so if you had an air bubble or a water vapor bubble in like a boiling pot of water, you would use this 2 gamma over R equation. But if you have something that's like a soap bubble, that's really the only practical situation where this happens, then you get 4 gamma over R as the pressure inside. And remember, that's a gauge pressure, so the total pressure will be that plus whatever's outside. Okay, so I know that's almost time for today. I just want to mention really quickly where this is relevant in biology, which is in your lungs. And so before we hop into that, if we had 2 of these droplets that were connected, the smaller one has a bigger pressure, so it's going to push water into the bigger one and cause it to continue to inflate until the small one is no more. So it's a really weird, almost positive feedbacky type of relationship where the smaller something gets, the more pressure it has. So it's going to dissipate that, which causes it to get even smaller, which causes it to dissipate faster. And so considering that your lungs are full of air pockets, this is really problematic because if those air pockets followed a similar principle, then they would get smaller and smaller and your lungs wouldn't work anymore. They would all vanish. You would just end up with one huge air pocket that wouldn't be very good at exchanging CO2 for oxygen, and you wouldn't be able to breathe anymore. So your lungs have a clever trick, which is they don't just use a water air boundary or something like that. They add some little fats into the mix, which are called surfactants. And so there's actually a condition if you have any relatives who have had like premature infants born, they often have trouble breathing because they don't have these surfactants. And as a result, literally by like once people figured out the physics of this, just by injecting them with some artificial surfactants into their lungs, you can allow them to breathe and literally save their life. And it's all due to this surface tension principle. And surfactants get around the problem of this positive feedback loop because as their concentration changes, as these bubbles change size, their surface tension gamma also changes. Okay, so that's where we'll leave it for today. We're almost done with surface tension. We just have to talk about wetting angle and capillary action, and we'll be done. Yep, 1 second.